Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 68, and this problem asks us to synthesize these following compounds using what we learned in this chapter and also in chapter 11 and 12, and we have some sort of restrictions on the reagents we can use. So we can use benzene, we can use 2-carbon alcohols, we can use ethylene oxide, and we can use any inorganic reagent. So let's start with A. So A, what we have, and also, one of the reagents we can use for the key one is acetylene, which is 3 carbons, right, like this. So in A, what we have is a benzene ring with 3 carbon with a 3-carbon triple bond directly benzyl to it, or off the benzoic carbon. So how you would approach to synthesize something like this is, well, we need to add a few carbons, and in the process of adding 2 carbons, we need to, I guess you could say, brominate both sides so we can get some elimination reaction and to get this triple bond. So the only source of carbons that we have is this ethylene oxide and these alcohols. So let's use this alcohol. So we know how to add carbons on benzenes when they have a leaving group on it, and that's with Friedel-Crafts reaction. So we know how to make this alcohol into a leaving group, being one of the halides, specifically chlorine, by adding SOCO to it. So now I made this into a leaving group, and then I can react this with my benzene in the presence of AlCl3, my Lewis acid. Then I'll get Friedel-Crafts alkylation to add those 2 carbons onto my benzene. And now from here, I can brominate the benzylic carbon, so then I can form a double bond, and then I can add bromines on either side of this double bond, and then I could oxidize both sides and eliminate both bromines so I can get my triple bond like I see in A. So let's brominate the benzylic carbon using radical initiator light. And now using a strong base, such as potassium tert butoxide, I can form a double bond in which then I can bromate both sides just with Br2. And then I can oxidize both sides using 2 equivalents of a strong base, such as sodium amide. And then I will get my doubly eliminated products, being this alkyne triple bond off of the benzene ring. And that actually gives us product A. So what about B? So B, let's draw B. So B, we have a triple bond, but then after that we have 2 more carbons and then an alcohol. So what we can say is that we need to get this triple bond just like in A. So this is A. And then after that, we need to make this into our nucleophile and attack the other source of carbon we have, which is this ethylene oxide group. And then we need to protonate the O- that would form to form the alcohol. So for B, we'll start obviously with the benzene, and we'll go through all of this to obtain the product for A. So we'll go through all of that to obtain the product for A. Now remember, there's a hydrogen here. Now we can deprotonate this hydrogen with sodium hydride. And now that's going to make a carbanion, which is going to act as my nucleophile, which then I can react that with my ethylene oxide. And 1, and then 2 with water to protonate the oxygen. Or 1, 2, and then we protonate our oxygen here. And this yields us with product B. So what about for C? So let's see for C. So C, we have a nitro group, and then we have 3 carbons, and then our triple bond. So what we can do is, well, we need to add 2 carbons, just like in A. And then once we add those 2 carbons, we need to add in, so carbon, adding these 2 carbons, they would be ortho and para directing. So then we can add our nitro group up to the para position. And then we need to continue working on these 2 carbons. So then what we need to do is, we know how to brominate the benzylic position, but we don't know how to brominate the terminal carbon here right off the bat. So then we would have to get our double bond, then go through some sort of Markovnikov's addition. So then we brominate the least hindered side, or the side with more carbons, with more protons. And then once we do that, we can add in acetylene to get this triple bond. So let's work through it, see what I mean. So we'll start from A, but we'll start from here from A. So in C, we'll start from the product of A from this position. And now these are an alkyl group, so they're going to be ortho and para directing. So then I'll add my HNO3 and H2SO4. Then I'll get 2 products, one being the ortho substituted, and one being the para substituted, which is my interest here. And then now I need to continue working on this. So let's brominate this using light and HNu. And the reason we're doing that is because I need to make an alkene double bond in which I can use HBr to do anti-Markovnikov addition, actually. So now I brominated this position, and then I can use a strong base such as potassium terbutoxide to make my alkene. And now I can use HBr and ROOR to do anti-Markovnikov's addition, if you guys remember. So now I have my bromine on off of this carbon. So now what I have is I just generated an electrophile with this carbon being the electrophilic carbon. So now if I add a nucleophile being this acetylene group, then I can do an SN2 attack and kick off this bromine and yield my final product. So now let me add acetylene. I'm going to react that with sodium hydride to now get a carbanion on one side. I'll react that with my electrophile, and then I'll get my final product here. So 1, 2 carbon, and then we have these 3 here. We have the NO2. So this is product C. So D, E, F, let's go to the next page. So let's start with D. So D, once again, remember your sources of carbon are very limited. So we have acetylene, we have this, and then we have our alcohol, and then we have our benzene. So these are all our sources of carbon that we can use. So for this problem, I think the easiest actually would be if I start with generating this acetylene off the benzene ring, like in A, and then like in B, I make this into a nucleophile, but now instead of attacking this ethylene oxide, I'm going to attack this product here because this is just will be an SN2, and then I'll make my product D, and then I can use a poison catalyst to make this triple bond into a double bond. So it's really fortunate that these are all interconnected somehow. So let's start with D. So I'll start with my product of A, my final product of A, being this. And now I will deprotonate this to make it into a better nucleophile. And then I will use this alcohol reacted with Sockle to get this, and I'll react it with that. So I'll react this nucleophile with this electrophile. This is step 1, this is step 2, and then I get these 2 carbons. So now all my carbon numbers are satisfied, but now I need to reduce this partially, not fully, to a alkene, not an alkane. So I need to use some sort of poison catalyst. So I'm going to use my Lin-Lars catalyst with hydrogen, and this is a poison catalyst. So what that means is that it's weaker than a regular reducing agent, such that it can't reduce alkyne all the way to alkane. It can only reduce it to an alkene, and that's exactly what we needed, actually. So now let's start with A. So, sorry, with E. So E, we have 2 carbons, and then we need to add 2 alcohol groups. Well, we know how to add 2 alcohol groups if this was an alkene. We just do ozonolysis, and then you would break this double bond and add 2 alcohols on double side. So we actually know how to do that already. So we know how to make this into an alkene. We've done this already right here. So let's add this alkene. Let's start from this alkene, and then we'll add the bromine, because this is also already ortho and para directing. So we can add the bromine, and then we'll do ozonolysis to add the 2 hydroxides. But first, I think we should actually add the bromines at this stage, because I think this is more ortho and para directing than an alkene. So we'll start from this molecule again, and then we'll add the bromine, and then add the bromine on the benzylic carbon to oxidize this, and then we can do ozonolysis. So let's start with this compound for E. Then we'll add the bromine at the para position. So remember, we will get 2 isomers, 1 at ortho, 1 at para. And we're just interested in the one in the para position. And now we can make this into an alkene double bond by doing the radical mechanism, like in B, H nu, then we add this benzylic bromide, and then we can add a strong base to, looks like potassium tert-butoxide. To make that alkene, And then we can do ozonolysis to break up this alkene to two alcohol groups. Remember the reagents for ozonolysis, H2O with sodium thiolate. Now we have our dialcoholic product here. So last but not least, we have C. So C, once again, we have carbon and then a halide pair to that, but now we have a nitro ortho to that. So what we should do is probably start with the same product as we started in E, add our bromine group to the para position, and then once we have the para position, we can add the nitro group to the meta or ortho position, and then once there, let's see what we can do. So once there, then we can make our alkene double bond, and then we can use MCPBA to cyclize this with the oxygen in it. So it's very important to know what your reagents do. So let's start with the same product as we started in E, or starting material we started in E. But now instead of adding bromine, we'll add chlorine. But we have the para and the ortho isomers. But we're only interested in the para isomer. And now this ethyl group is going to be directing here. So then we can add our nitro group. Now we need to make an alkene double bond before we can use MCPBA. So let's add our bromine, our radical initiator, and then 2, we'll just add the strong base, potassium terpetoxide, to get our alkene, just like in E. And now from this stage, if you guys remember, I think it was chapter 11, maybe chapter 12, if you had CPBA, you convert your alkene into a cyclopropyl group with an oxygen in it. Just like this. And that gives us product F.